Morning, students. Myself, JNTUK from AC Department, Chevrolet Engineering College. Today, we are going to discuss about the same topic of orthogonality concepts. In yesterday class, we completed the orthogonality in vectors, orthogonality in signals, orthogonality in approximation signals, orthogonality in complex signals, and some part of the mean square error also. Let us see the mean square error again. The mean square error. So let us consider a mean square error in signal approximation using orthogonality function. The error energy is given by the equation. The error energy given by the equation is ER is equal to or EE is equal to whatever it is, integral T1 to T2 f of t minus sum of n is equal to 1 to n Cn xn of t whole square into dt. Expand this function is a square minus b square, not the a square minus b square, a minus b whole square, a square minus 2ab plus b square, and split the integral of three parts. Integral T1 to T2, the a square is f square of t by dt, f square of t into dt, minus 2 into ab. A is f of t and b is the sum of n is equal to 1 to n Cn xn of t, plus and integral T1 to T2, sum of n is equal to 1 to n Cn square xn square of t dt. Okay. Interchanging the order of the summation and the integrations. The first part you can see there is no any changes here. The integral T1 to T2 f square of t dt, the same thing. And the remaining function in the second term, we can see the same expression here. You see the Ci is equal to integral T1 to T2 f of t xi of t dt and integral T1 to T2 xi square of t dt. So this is a denominator function. You can assume that as EI because I is there here, EI, and cross multiply it becomes of CI into EI. Okay. Or the I is a variable only, you can replace that as Cn into En. So that is equal to the function of integral T1 to T2 f of t and xn of t dt. Got it, my dear friends? So I replace that integral T1 to T2 f of t xn of t dt function as Cn into En. Okay, and the denominator, whatever I am saying, that it is En is equal to integral T1 to T2 xn square of t dt. So here the another integral is there. Replace the integral T1 to T2 xn square of t dt as En, and this function is replaced with Cn into En. Okay, now okay. See the error energy E is equal to integral T1 to T2 f square of t dt minus 2 into the sum of n is equal to 1 to n Cn. I replace here the Cn and En. And for this function, Cn square is already there. And now the value is for integral T1 to T2 xn square of t dt is En. Okay. That is equal to, simplify this equation, integral T1 to T2 f square of t dt minus sum of n is equal to 1 to n Cn square En plus sum of n is equal to 1 to n Cn square En. So here the minus 2 and here the plus 1. So totally you get the minus 1. The combination is sum of n is equal to 1 to n Cn square En plus integral T1 to T2 f square of t dt is EI. E, not the EI. E is equal to. So E is equal to, we got the integral T1 to T2 f square of t dt minus sum of n is equal to 1 to n Cn square En. So mean square error is E square of t whole bar is equal to, the formula is E error energy by the T2 minus T1, the difference between of the upper limit and the lower limit. Substitute this function E and divide with the T2 minus T1, we'll get the error energy signal. not the error, mean square error. So the mean square error and the error energy are related as E square of T whole bar is equal to E by T2 minus T1. So for totally substitute the E is equal to integral T1 to T2 F square of T dt minus sum of n is equal to 1 to n Cn square En by the T2 minus T1. So in the above equation, Cn square En is always a positive. Hence, error energy EE can be reduced. Always a positive means definitely it is subtracted from this function. If it is subtracted, the function means and still it is a decreases. If it is a decreases means the mean square error. The E is equal to also the total function E is also reduced with the number of terms n is used for representing or increased. Okay, only the numerator E is reduced when the Cn square En is always a positive value. So ER tends to 0 when n tends to infinity. When n is increasing, the E is equal to tends to 0. Under this condition, the orthogonality set is said to be complete. Under this condition, the orthogonality signal set is said to be complete. So complete set of orthogonal function. A complete set of orthogonal function means the error energy signal having the second term is there. That second term is always a positive value. As n is increases, error energy is decreases. N is increases, error energy is decreases. Thereby, the mean square is also decreased. Under this condition, the orthogonal signal set is said to be complete. See, the closed or complete set of orthogonal function means it is a 0, means the value is a 0, the mean square error. Why it is a mean square error is a 0, error energy is reduced. How the error energy is reduced? By increasing of the n value. And the total term, the second term, always a positive. Always is a positive value. So equate to the 0, 1 by T2 minus T1, integral T1 to T2 F square of T dt minus sum of n is equal to 1 to n Cn square En with the mean square error is a 0 as of n tends to infinite. Because of this function is increases, the term is positive always, then error energy is reduced and mean square error becomes a 0. So the integral T1 to T2 F square of T dt is equal to the sum of n is equal to 1 to infinite Cn square En. With the n approaches infinite, the 1.1, so finally the previous expression it is always the value is a 0, reduces the value. A complete, then this condition we can call it as an orthogonal signal set is said to be complete. So the f of t is equal to, this is a function integral t1 to t2, the sum of value is there. Now the f of t, if I am taking this orthogonality function, any orthogonal function f of t is equal to sum of cn into en is equal to, let this value is here x1, x2 and so on is a set of mutually orthogonal function. It is said to be complete or closed set if there exists no function of the p of t for which. So I am taking this function as the p of t. Why I am taking the p of t? So the f of t, instead of f of t, if I use p of t, the orthogonality of approximation signal is integral t1 to t2 f of t xn of t dt. So the p of t, when n is equal to 1 to n, the p of t exists and above integral value is 0, then obviously the p of t must be a number of set xn of t. So here I am taking the set of mutually orthogonal signals xm of t and xn of t is equal to 0 for m not equal to n and en for m is equal to n. Having the f of t having the different points on the x-axis, that is c1, x1 of t, because x1 of t is one of the signal. and another x2 of t on the x-axis, another point xn of t, and so on xn of t, and so x3 of t is also the another point on the x-axis. Okay. So the f of t, and we have, let us take is c1 x1 of t. Another point, if I assume c2 x2 of t, and so on. When this function becomes a 0, then only the total set, completely set of orthogonal function is c1 x1 and c2 x2. So the ci is equal to, or cn is equal to, because you know the cn, it becomes of cn, xn, and xn square of t. So integral t1 to t2 f of t xn of t dt, and integral t1 to t2 xn square of dt. And denominator function is energy signal, so the energy is En. So Cn is equal to 1 by En into the integral of t1 to t2 f of t x I of t, nothing but xn of t. This is called generalized Fourier series. Generalized Fourier series, and Cn is given by the above equation. The set of xn of t is called orthogonal basis function. Okay. And orthogonality complex function we already seen. Any one we can keep as a complex function, xm of t and xn star, or xm star and xn of t. When not equal to n, the value is always a 0, and this function, the given signals are orthogonal. And when m is equal to n, the given signal is an error energy signal. F of t is equal to sum of. If f of t can be expressed as sum of n is equal to 1 to n infinite as cn xn of t. Cn xn of t, where the cn is equal to 1 by n. Any one is a function, is a complex function. Any one is a complex function. In the denominator also, the energy signal is xn square of t. In that, xn of t and xn star of t, the magnitude of it. Magnitude. Got it, my students? For trigonometric Fourier series, we derive that function is, we derive the function, the complete set of orthogonality. See the integral t1 to t2 f square of t is equal to sum of n is equal to 1 to infinite cn square en. And other way, f of t is equal to, the f of t is equal to cn. The f of t can be expressed as orthogonality complex function. F of t is equal to sum of n is equal to 1 to infinite cn xn of t. And that function, if I am using here to find the trigonometric Fourier series, f of t is equal to sum of, or otherwise, if you are confusing, let take a right angle triangle, assume this signal is f of t. There is an error signal e of t, and here there is a xn cn of t. Hypotenuse side is equal to the side plus side. What is f of t is equal to e of t plus cn into xn of t. Okay. So error is energy is 0. To find the trigonometric Fourier series, these two are perpendicular to each other. There is no any error. So f of t is equal to, where n is equal to 1 to n means take it as a sum of n is equal to 1 to capital N cn xn of t. Okay, to find the trigonometric Fourier series, use this function. So f of t is equal to sum of n is equal to 1 to n or 1 to infinite. When this infinite, then only we can say it is a complete set of orthogonal, or is also called as a generalized Fourier series. A orthogonal signal set xn of t, and this equation is called generalized Fourier series. We have seen that the set having the 1 cos omega naught t, cos 2 omega naught t, cos n omega naught t, and so on. This example we did in the class itself, my dear students. Okay, 1 cos omega naught t, cos 2 omega naught t, cos n omega naught t, sin omega naught t, and sin 2 omega naught t, and sin n omega naught t. is orthogonal over the period T naught. Here omega naught is called fundamental frequency and n omega naught is the nth harmonic. There is a DC component of cos n omega naught at n is equal to 0 and cos 0 omega naught is equal to 1. The value is 1 here, my students. This signal set consists of sine function and cosine terms, hence it is called trigonometric set. Trigonometric set. So f of t is equal to, let this f of t, but this set we can written as f of t is equal to a naught, a1 with cos functions and a2 with cos functions and so on, plus b1 into sine functions, b2 into sine 2 omega naught t and so on. So actually the a naught is also multiplied with the cosine function. That cosine is cos 0 omega naught t. The value is 1. Okay. So a coefficients is multiplied with the cosine functions and b coefficients is multiplied with the sine functions to derive the trigonometric Fourier series function. Okay. So then it becomes a naught plus here the a1 cos 1 omega naught t, a2 cos 2 omega naught and so on. Keep that is a sum of n is equal to 1 to infinite. Plus the second part is sine is multiplied with the bn functions. So bn sine n omega naught t, b1 sine 1 omega naught t, b2 sine 2 omega naught t and so on. Okay. Then the values of a and bn can be obtained from the equations. This is the equation for the orthogonality function, my dear friends. An means the cn value. Cn is equal to integral t1 to t2. So integral t1 to t2, now I am taking as integral t to t plus t naught. Why this means if the t is equal to 0, t naught is a pi, is a full cycle. In a full cycle, I have to represent this as a t to t plus t naught f of t x n of t dt, and the denominator integral also t to t plus t naught x n square of t dt. Okay, I'm changing this as a cn as a an to find the an values. Okay, what is the f of t and xn of t? Xn of t you see here the xn of t represents the orthogonal signal set. Orthogonal signal set. So I use here the orthogonality signal set as the functions of cosine there. For an is multiplied with the cosine. So xn signal is I take the cos n omega naught t dt and denominator also replacing cos square n omega naught t dt. Okay. Similarly, here you can see the Pn is equal to the same expression integral t to t plus t naught f of t xn of t dt by the integral t to t plus t naught xn square of t dt. But xn of t replacing with the sine function. Sine n omega naught t dt and here the sine square n omega naught dt is a Pn. Cos n omega naught t and cos n square omega naught t is a An. Okay. Now simplify the expression in the denominator here. Cos square n omega naught t. Cos square theta is, you know the cos square theta. Cos square theta is 1 plus cos 2 theta by 2. So what is a theta here? N omega naught t. So 1 plus cos 2 n omega naught t by 2. So split the two parts of the integral here. See, this is a function already there. And 1 by 2 the integral t to t plus t naught dt plus 1 by 2 integral t to t plus t naught cos 2 n omega naught t dt is also there, my students here. Here note that the second term is integral of full cycle of cosine function over one period. It is 0 always. I already told in a full cycle cosine function or in a full cycle sine function is a 0. Simply say. So integral t over 2 t plus t naught cos square n omega naught t is equal to 1 by 2 t. Here this function is a 0. So integral dt is a t, upper limit is t to t plus t naught, and lower limit is a t. So t plus capital T naught minus t get cancelled. We have the t naught by. So denominator an is equal to, in the an, the denominator got as t naught by 2. So finally the an is equal to 2 by t naught integral t to t plus t naught f of t cos n omega naught t dt. The an function. Okay. And similarly, the Bn is calculated. The Bn is equal to, instead of cosine function, you can use the sine here and simplify the trigonometric function, the denominator, integral t to t plus t naught sine square n omega naught t dt. Sine square n omega naught t dt. What is the sine square n omega naught t dt? 1 minus cos 2 theta by 2. Got it, my dear students? What is the sine square n omega naught t dt is? Cos square is a 1 plus, sine square is a 1 minus 1. Even it is a cosine function is in the full cycle is a 0, 1 minus 0 or 1 plus 0, both are the same. So here the denominator part of cos square n omega naught t dt in the interval of t to t naught is 2 by t naught, and for similarly the integral t to t plus t naught sine square n omega naught t dt is also the 2 by t naught only. Okay. Then see here an we got to 2 by t naught integral t to t plus t naught x of t cos n omega naught t dt, and bn is equal to 2 by t naught integral t to t plus t naught x of t sine n omega naught t dt. So what is the a naught? A naught means replacing n is equal to 0. So cos 0, what is the cos 0? 1. So, and integral t to t naught x of t cos 0 is a 1 and dt. Now here it is a 2 by t naught, my dear students. Actually it is a 2 by t naught means in this expression it is a by 2. Okay. You can use here the 2 by t naught. Otherwise, in this function there is a 2 by t naught, and by replacing of n value is a 0 means definitely this value is a 2 by t. 2 by t naught. Okay. If here it is a 1 by t naught means change this value is a naught by. Both are the same. So this total set we can call it as a trigonometric Fourier series. Trigonometric Fourier series. Got it, my dear students? An function is for cosine function and the bn is for the sine function. Understood? And convergence of Fourier series in the discrete conditions. There is a 4 discrete conditions we have. The Fourier series is convergent in the signal x of t satisfies some conditions. These conditions are called discrete conditions. The first one is, it is a single valued property. Single valued property. So x of t must have only one value. The x of t have only one value at any time instant within the interval t naught. Within the interval t naught. And the second one, it having the finite discontinuities. Having the finite discontinuities. X of t should have at the most finite number of discontinuities in the interval t naught. Because of this, the signal can be represented mathematically. So the second condition is it having the finite discontinuities. X of t should have at most finite number of discontinuities in the interval of t naught. And third one saying that finite peaks. The signal x of t should have finite number of maxima and minima in the interval t naught. The second condition is saying that x of t having the most finite number of discontinuities in the interval of t naught. Third is saying that finite peak. And it also having a finite number of maxima and minima maxima and minima in the interval of t naught. And the fourth point is a very important point here. It is absolutely integrable. Absolutely integrable means the value is a finite. That value is finite means the integral t to t naught or the t to t1 or the any values of the t is less than the infinite. See here, it's absolutely integrable. Integral t naught, the magnitude of x of t is infinite, less than the infinite. The signal x of t should be absolutely integrable. This is because analysis equation integrates x of t. So if these 3-4 conditions are the discrete conditions, the above conditions are sufficient but not necessary conditions for Fourier series representation. Whatever we are discussing now, the 4 conditions are there. It is sufficient, but it is not the necessary for the Fourier series representation. Most of the physical signal satisfies the above conditions. Most of the physical signal satisfies these above conditions. Okay, this is a very important, my dear students. In part A, definitely they ask what are the 4 conditions or what are the conditions we have for the Fourier series that we can call it as a discrete conditions. Okay, and the analysis Fourier series is used for applicable only for the periodic signals. See this explanation part of the discrete conditions. So the function x of t is a single valued function. Single valued function. That is, the function x of t must have a single value at any instant of time. Having only single value, any instant of time, you can take any value of the time, having only single value. For example, consider the 4.1 here, the double valued means at t naught, we have the plus value and the minus value. Okay, plus value and the minus value. But according to this, we are saying it is a single value term. So for the example 4.1, which is not a single value because it has 2 values at t naught. What are the 2 values here? The positive value is there here and the negative values also. So see in the section figure P, it is a single value. At t naught, we have only one value. And let us see here the t, another function is there, the t1 here, and t1, t minus the t naught before the value of t naught and after the value of t naught also, having only the single value. If there is a single valued function, that is also satisfied, the first ones. The function x of t is a single valued function, means is a way we are taking the double valued and the single value. Double valued means for one value there is a two values, 1 plus 1 and the minus values. Okay. The function x of t has a finite number of discontinuities. A finite number of discontinuities. That is the second condition. Consider the figure 4.2a. It has no finite number of discontinuities. And it is not possible to find the value of function x of t at such a number of discontinuities. Hence, it cannot be represented as a Fourier series. Okay. What they are saying, it is having a finite number of discontinuities. Finite number of discontinuities. In the figure A, there is any finite number of discontinuities. Okay. And figure 2C, the finite number of discontinuities. Means at the t, it is again the 0 and it is repeated at the regular interval. The function shows in the figure 4.2b has a finite number of discontinuities, and the value of x of t at the discontinuity can be calculated by using this formula. X of t is equal to t, x of t minus plus x of t plus by 2. The range is there. So the function x of t has a finite number of minima and maxima. Finite number of minimum and the maximum. Okay. There is no any discontinuities here. The first function, it having some discontinuities, finite number of discontinuities. It satisfies the second point or second condition. And the third point saying the function x of t has a finite number of minima and maxima. Minima and maxima. The function shows in the figure 4.3a has no fixed number of minima and maxima, so it is cannot be represented as a Fourier series. So if the first one, it is not the Fourier series, and it is also not satisfies the Fourier series. It satisfies the Fourier series, and it is also satisfied. And second one, third one, third one, minima and maxima. You see here, a finite number of minimum and maximum. In this, the function having no fixed number of minima and maximum. So minimum value, there is no any fixed number of maximum and the minimum, but fixed number of maximum and the minimum is there, plus a minus a, and here the plus a and minus a. Got it? So the second function, whatever it is representing of the Fourier series. It is not representing the Fourier series. Okay, means it shows the x of t goes on increasing, and again it is a decreasing and decreasing cycle. But here there is a fixed maxima and the minima, fixed maximum and the minimum. Got it? And the fourth function saying that is absolutely integrable. The function x of t is absolutely integrable with the t1 to t2, the range of interval. The figure shows here it is not absolutely integrable within the interval of t1 to t2. So here the exponential function we are taking, as it is cannot be represented as a Fourier series, but the function showing in the figure 4.4b is absolutely integrable for the interval of 0 to t. The integral 0 to t, the magnitude of dt is less than infinite. But here the exponential goes on increasing. Okay, it is not the less than the infinite, and hence can be represented as a Fourier series. So second function. Got it, my dear students? Okay. Then next is a very important topic is a Fourier series. Properties of the Fourier series. See in the next class.